Hey everyone, and welcome. Today, we are going to dive into one of the most fundamental and honestly, one of the weirdest ideas in all of quantum mechanics. We're going to see what happens when you trap a single particle in a tiny box. And trust me, the answer is not what you'd expect, and it pulls back the curtain on a fundamental truth about how our universe really works.
All right, let's get right into it. To start, we need to set up the big mystery we're about to solve. It all kicks off with a really simple question that leads to a totally shocking answer. So just imagine this for a second. You take one single electron, and somehow you trap it inside a super tiny, one-dimensional box. It cannot get out. It can only zip back and forth along a line. What do you think it does in there? How does it behave? Well, this is where our everyday intuition just completely crashes into quantum reality. See, based on the world we see, our common sense says the electron would just bounce around randomly, right? It could have pretty much any amount of energy it wants. But quantum physics says, nope, not a chance. It tells us the electron is only allowed to have very specific, discrete energy levels. It can't have just any energy. It's an incredibly strict rule. So, how is that possible? Why would that be true? Well, to get to the bottom of it, we first need to lay out the ground rules for our little thought experiment. You can think of it like setting up the game board before we start to play. The official name for this puzzle is the particle in a one-dimensional box, and yeah, it's pretty much what it sounds like. We've got a particle, it can only move left and right along a single line, and it's trapped between two walls that it can never, ever get past. And this whole scenario works because of three pretty simple assumptions. First, inside the box, the particle is totally free. Nothing's acting on it. Second, we just say its potential energy inside that box is zero to keep things simple. And third, this is the big one, the potential energy outside the box is infinite. That infinite energy wall is what makes it absolutely inescapable. The particle is stuck in there for good. Okay, so we've got the rules of the game set. So how do physicists actually figure out what the particle is doing? Well, they pull out the most powerful tool in the entire quantum toolkit to solve this puzzle. Now, whoa, don't let this equation freak you out. This is the famous Schrödinger equation. But for what we're doing, just think of it as the master rulebook. It's the fundamental equation that describes how this particle has to behave. We're not going to solve the math, but we are going to look at what the solution tells us. You know, the key to cracking that master equation actually comes from something called boundary conditions. And the logic is super simple. Since we know for a fact the particle cannot be outside the box, its wave function, which is just a way to describe the odds of finding it somewhere, has to go to zero right at the walls. And that simple logical rule is what forces all the weird quantum stuff to happen. So when you take those simple rules, those boundary conditions, and apply them to that master equation, a very specific and really profound solution is forced to pop out. Let's take a look at what nature's quantized answer actually is. And there it is. That's the solution. This one elegant little equation tells us every single allowed energy level for our trapped particle. Here, n is just a whole number, like 1, 2, or 3. H is a constant of nature, m is the particle's mass, and L is just how long the box is. This is the answer to the whole puzzle. So what's the big deal with this equation? Well, what it proves is a concept called quantization. It's the idea that a physical thing, like energy, can't just have any value it wants. It's not a smooth ramp, it's a set of stairs. The particle can have the energy of step 1 or the energy of step 2, but it can never exist at an energy of, say, step 1.5. Now check this out. Let's look at the lowest possible energy state, when that number n is just 1. We call this the ground state. Do you see something funny? The energy isn't zero. That means even at its absolute minimum energy, the particle is still wiggling around. It can never be perfectly still. This minimum possible energy is called the 0-point energy, and it's a fundamental part of our universe. Okay, I know that's a lot to wrap your head around. We've got a formula, we've got quantization, 0-point energy, but let's zoom out for a second and connect the dots. What are the big takeaways from all this? Why does it matter? So this one simple thought experiment actually reveals 4 incredible things about how reality works. First, we've established it. Energy comes in discrete packets. It's quantized. Second, those energy levels get farther and farther apart as you go up. Third, and this is so cool, if you make the box smaller, if you shrink L, the energy levels go up. The more you squeeze a quantum particle, the more energy it has. And fourth, as we saw, the particle is never, ever truly at rest. And I really want you to know, this isn't just some abstract physics puzzle. This whole principle of trapping a particle is the foundation for amazing real-world technologies we use every day. It's crucial for things like quantum dots, which give those fancy new TVs their incredible colors. It's at the heart of nanotechnology and basically all of modern semiconductor physics.
So, if you take just one thing away from our little explainer today, let it be this powerful idea. The smooth, continuous world that we see and feel around us, it's kind of an illusion. When you zoom in far enough, down to the microscopic level, you find out that nature isn't continuous at all. It is, and it always has been, quantized.